All right, so let's go on to the next question. So prove that every odd integer is congruent to 1 modulo 4 over 2 3 modulo 4. So assume A is an odd integer. Apply the division algorithm. And divide A by 4. And then what you get is A is 4 times Q plus R then we have that since A, so you could write this as follows. This you could write this as 2 times Q prime plus R, where Q prime is 2 times Q, as that will give you 4Q. And here we cannot have any R being an even number, because then A would be even. So in particular, we cannot have 1. We cannot have, so it cannot be, so it can be 1, but it cannot be 0. It cannot be 2, and so it cannot be 0 and it cannot be 2. So it could be 1 or it could be 3. So that's the main idea. So A is congruent to R mod 2. So R must be odd. All right. Let's move on to the next question. So question 9 tells the following. Prove that A n minus A squared is congruent to A squared mod n. So let's do this problem really quickly. So here you could expand n minus A squared and then what you get is n minus a squared is equal to n squared minus 2 times a times n plus a squared, and that is all the n is congruent to 0 mod n, right? Because they're multiple of n, so everything is congruent to a squared mod n. Similarly, for part B, we have that we want to prove, for part B, we want to prove that 2 times n minus a squared, this is congruent to a squared mod 4n. So let's show that. So 2n minus a squared, this is um 4n squared minus 4n times a plus a squared, and 4n squared is congruent to 0 mod 4n, as they're congruent to 4n, and similarly minus 4n a is congruent to 0 mod 4n, and so we get a squared mod 4n. Let's look at question 10. So if a is a non-negative integer, prove that a is congruent to its last digit mod 10. Yeah, so let's solve this problem. So assume that a is non-negative integer, we can write any number as multiples of 10 raised to some power, and we can see that the last digit doesn't have a multiple of 10 in it, as it's 10 to the power of 0, and then everything vanishes except the last digit. So you could see it in that way. You could also see it by the division algorithm. So then apply the division algorithm, then you get that a is equal to 10 times q plus r, where r is between 0 and 9. So then that means that a is congruent to r mod 10, and what is the guarantee that you get that it is the last digit? Well, the guarantee is that you can always subtract multiples of 10 and then from the number, and then once you reach certain subtraction, you arrive at the last digit. So you can prove that this R is really the last digit of the number. Or like, yeah, exactly. So that's the main idea. So let's solve the next question. So the next question says the following. If A, B are integers such that A is congruent to B mod P for every positive prime P, prove that A is equal to B. So if A is not equal to B, then this tells you that A minus B is strictly bigger than 0, and we have that P is a factor of the integer A minus B, which belongs to Z for every P. For every P, which tells you we cannot write A minus B as products of finite primes, which contradicts the prime factorization theorem. So yeah, I hope you guys enjoyed this video, and I will see you in the next one. We'll solve more problems. See you guys.